So I will present some work I've been doing concerning interfacing root directly with TensorFlow to build pre-processing pipelines for machine learning. So to start, this notebook I compiled together works with Python 2.7 and these TensorFlow keras and root versions. And mostly it just relies on binaries that are taken from Anaconda, CondaForge repositories. So to start, as an introduction, so common machine learning frameworks like PyTorch or TensorFlow, keras, MXNet, scikit-learn, XGBoost, they all require usually that the data for the training is typically in the form of an NumPy array or pandas data frames or similar Python types. And it's therefore very convenient to store actually the training data as either NumPy arrays or even HDF5 files. However, and so to give you an example, so this is like the hello world of typical machine learning to classify handwritten digits from images. So I will just give you this example where first you can download this open dataset. And it will be loaded completely into memory, and this is only a very small one, about 50 megabytes for the training. And then we just need to do some pre-processing to set up essentially the classes, and also I will only train here on the first 1000 images, just for speed. And after setting up a simple neural network, so this is just a simple convolutional neural network, you can see its structure here. And then we can train it, and this works like this. That one then essentially gives this NumPy arrays that are loaded into RAM now, just to the keras fit function to fit essentially the model. You can see this working just now, so I just train it here for 2 epochs, but of course don't take this example very seriously. I mean, clearly there's the amount of batches and also the amount of data used here for the training is clearly not enough to give you a realistic classifier for these, but this is just for demonstration purposes. So you may now wonder, okay, I used keras here to train this simple neural network, but how does actually TensorFlow, the underlying backend for keras, in this example gets the data? And the magic is happening behind the scenes, so in this fit function. And the way this works is essentially that in TensorFlow, it constructs a graph, and it places the input as a placeholder. And then when you then execute essentially the output node here called output, which is the probability that a certain image corresponds to a certain handwritten digit, you need to feed in this tensor. So the data is now that is held in memory is directly fed via this mechanism here via placeholders to TensorFlow. So as a summary of this simple example, I showed you just the basic ingredients for constructing and training neural networks, and the data set being completely held in memory, and the form is an NumPy array in this example, and TensorFlow gets the data through the placeholders. So then I come a bit to the physics side first, before going to more examples. So one very nearly classical example of machine learning in collider physics is you want to classify essentially the jet origin, or the origin of a jet, where a jet is like a collimated spray of particles. You can see here an example event display from the CMS experiment where these particles, or many of them, line up in these yellow cones, which are the jets, and these have been reconstructed with the INTKT algorithm. And now you want to know, okay, what is actually the origin of, or what caused these jets to appear? And these can be various sources. So for example, you can have just simple quarks, B or C quarks, UDS quarks, gluons, or also more complex topologies. For example, you can have boosted W bosons or even top quarks, where all, due to the high boost, all of these decay products are found within one fat jet, essentially. There have been several algorithms developed to tackle this problem over the years. Just giving you a few ideas what are the latest ones in these two publications there. And typically the inputs that are used are the global jet features. So this means the kinematics, but also then the secondary vertices, because usually if you have a B jet, for example, these have a finite lifetime, so they can travel a certain amount before actually decaying, so they will cause a secondary vertex often. And then also more modern or recent algorithms, they even go very deep inside the jet and even use the raw clustered particles, meaning the charged tracks or the neutral energy deposits recorded by the calorimeters. So in the second example now, I use here a simulated QCD event, a sample from the CMS open dataset. And now I'm showing you how one can train this algorithm, now using the data stored instead in a simple root 3 tree. So I will be using uproot here. So you see here I have about 20 files that I already where I already store these input variables I want to use, and then we can just have a little look. So there's like 1,200 jets per file, and then we can also plot a bit of the features and also the the input features that are used for the training, but also the labeling of the jet. So that is actually what you want to infer through your machine learning. So here you see, for example, that the tens jet here, so there's a U or D, it comes from a U or D quark, and then it's global PT, eta, or also here NSV means number of secondary vertices reconstructed in that jet. And of course there can be 0 because this reconstruction is not perfect, but there can also be, of course, more than 1 if there is also ambiguity there. But just feeding everything of these into a machine learning classifier, it can figure it out pretty well how you can tag these such kind of jets. And now to train on these root trees, I just show you how to use this generator pattern, where you first write a generator. And I'm using here, as I said before, uproot to just create now batches by looping first over the files and then also over the batches I want. And then essentially I make an NumPy array where I basically stack up the features I'm interested in for training. And this is just an example here showing you, okay, if I select here, the features I was showing you before. So meaning here's the global PT, eta, NSV. These are the first vector here. This is my input vector. And then the second here is already the one hot encoded, essentially target. So the labels I want to infer. So one cannot train a simple neural network to classify these jets. Again, building your simple, fully connected model with keras. And then one can now use this fit generator function from keras and directly give it the generate function we just wrote. And this works very well. So it will automatically read the files, loop over the files, and then also produce the batches of the features you want. And to recap this example now, the data is read sequentially from this using this generator pattern. The advantage is now here that one can now work with arbitrary large data sets. So not everything is loaded into memory at once. And it also does not really dictate what kind of decoder you use to actually read and decode the raw inputs, the byte streams. And here I showed you how to use this uproot very easily. And it also allows you very simply to select features, or also to do, of course, pre-processing if you want inside this generator function. However, it has some disadvantages. For example, first of all, it's I/O limited now, because usually it's just serial, meaning that the training may need to wait until the data is actually being read from disk and then also processed and then loaded into RAM. And there's also no real shuffling of the batches. So usually one wants to perform a bit of shuffling of the input data per epoch, which also helps to prevent overtraining or overfitting of your network. So this is kind of a bit of a drawback from this method. And the obvious solution one can then do is instead to read the data actually from disk asynchronously and then populate some kind of cache. And then you can try to randomly select the batch from this cache to train on. This would actually solve all these problems. However, in this case, one really needs to deal with threads and also points of synchronization, which is usually a bit of complicated for the average user. So TensorFlow 1.x allows actually to build complex input pipelines using queues, using a queue system. And the idea is here that you build a system of two queues. The first queue just holds a list of file names you want to read in. And then there are several parallel operations that try to read in the files and decode the data, and then enqueue these converted data that are converted into tensors into the second queue. And then from the second queue, you can essentially just select a random batch that you can then dequeue for the training. However, the problem now is that there is no real, of course, native operation to read root tree trees in TensorFlow. So first, to give you an example how to actually work with queues, this is very simple. So this is just an example where you define like a FIFO queue, where you give it its types and shapes. And then this is like the first example I want to show you. And then you can define enqueue and dequeue operations. And also you cannot even enqueue one element, you can even also enqueue many, or the same way you can also dequeue many. And just to show you, so I'm just populating this queue with the values of 0 to 9, and then I'm dequeuing a single event, so I also can dequeue just 4 in a row. You see here, since it's just a FIFO, it's just all in order, but I also can switch this around and essentially use a random queue now, and this gives me a random output here. So this is just a primer for how to deal with queues in TensorFlow. So now we need, of course, this reader to interface with the queue system. And I've written this in C++ as a plugin for TensorFlow, which is then linked against root to read T-trees. And I'm using here CMake to compile this plugin. So this takes a bit, unfortunately, on Binder. Just bear with me. Okay, so we have created a make file, then we can build it and install it. And essentially, when this is done, hopefully soonish, one can simply append this the install directory to the Python path, and then one can essentially import this plugin like a normal Python plugin, Python module. So now we have this TensorFlow operation to read root T-trees, and now we just need to set up this simple as a pipeline. So the idea will be first, as a simple example, to construct the file name queue as seen before, then add the root reader now to dequeue, decode the data, and then enqueue tensors into a random batch queue, from which we can then start the training. So the idea is here is just a simple pipeline, not to replace usually all of these operations on the CPU intentionally, because you want the GPU to be free for the training. So the training is done on the GPU, while CPU performs in parallel and asynchronously all these pre-processing and loading of the data, so that these don't interfere with each other. So first, constructing this random list of file names, there's just this convenience function one can use. Then there's this custom root reader I just compiled, and it will automatically dequeue from this first queue and then and produce tensors. And these are then essentially enqueued into the second queue, which is also a random batch queue. And you can see here it also accepts even more than one reader, so it can randomly even select from which one it will draw the data. And yeah, it has some capacity, also the seeds, and yeah, we will also use the fact that we will not read just one after one jet, but even enqueue many all at once. So work now. So then the advantage here of this root interface is that one can very easily now define what branch names one wants to read. And the first feature edit, I call it here, just reads these global branches, again the PT, eta, and number of secondary vertices, which I select here, and then you just specify the file list, a list of files you want, and then you can essentially in a TensorFlow session create a simple pipeline. And executing this, one can, one sees then that indeed when one calls this batch now here, which is essentially, which will then automatically, as an operation, it will automatically dequeue from this random batch cache. And you can see here, okay, we get, first of all, we get this global array, and also here just for debugging purposes, just to check of the number of events or number of jets inside the file that were read. And you see that these are pretty much randomized as intended. So then one can, however, also be more creative here, also define more than one array that is produced, and also even internally it's using this T formula to interpret these branches, so one can even chain them up. So for example, here one has multiple sub-labels for bjet, but one can just, for simplicity here, all of these categories together to get just one big one. Executing this gives you exactly the desired output. So here you see also an interesting thing that for the secondary vertices, since there can be many of them, one needs to specify how many one will maximally read or want to read, and the rest, and it will always be zero padded. So you see here that, for example, in this third, a jet here has one secondary vertex, and you see here that indeed for this line here, that only there the features are filled, while the rest is zero padded. So then last example, I just want to show you, one can even go a bit more extreme now. One can even now define multiple parallel readers to populate the tensor queue, and then even perform some pre-processing on the tensors. And what I will do here in this example is just perform random sampling. And the idea is to achieve the same PT and eta distribution per jet in such a way that one reduces the bias. So the neural network is actually forced to optimize each PT and eta point, which is a common strategy for such jet attackers. So we see here, I'm just loading under the hood a huge feature dictionary as seen before, where you have various groups now. So you have charge candidates, neutral candidates, global variables, the truth level, or the secondary vertex features. And you see here, these are like either two-dimensional or one-dimensional. And then for the resampling, I'm creating first root histograms that tell me, okay, how one needs to either up or down sample a certain class of jet to achieve essentially a class balance as a function of zeta and eta. And you see here the applied resample weights essentially for the different classes. So in this case, B-jet, C-jet, UDS, or G as a function of the PT of the jet. And of course, again, this is just an example. So a weight above 1 means essentially it will be upsampled, but in general, you should really avoid this because it can cause overtraining or overfitting of your network rather quickly. But one can always prevent this by using just a very large larger data set. So then to build the pipeline, again, we construct the first queue of the file names. Then we define in a loop multiple readers. And then we define here the weight first, that is essentially read from the weight histogram stored in a root file. And then one can apply this resample function, which essentially will create multiple of a certain jet features or not, or even remove multiple ones in such a way that in the end you hopefully end up with equal distribution in PT and eta of all your classes. And to train now the neural network, I do essentially the same thing as Keras fit function does under the hood. I just feed in here these tensors from the queues directly into Keras input layers, and then create a bit of a more complex model as well. We can have a look maybe later if there's time into the details. Define the loss function, optimizer, and then initialize everything. There's these coordinators now in the thread queue runner that will automatically spawn enough threads for the queues to be filled. So since we are now reading the input files in parallel, and then these root readers, for example, will all run in parallel, and then they will automatically synchronize themselves to enqueue the decoded tensors into the cache. And yeah, so you can essentially run this. So it's just this warning about the range. You can ignore that. And this runs for about 1100 steps. Again, just ignore here the loss function. In this example, again, I'm using far too little training data to be realistic. But here you see now this is just a plot of the used batches. The PT essentially plotted for each class separately, and you see indeed your B, C, UDS, and G class, they all have the same shape. In this case, a flat shape. That is what we desired in this example. And yeah, for example, if I change it now here, instead of using these resamplers, I just comment this out using directly the reader, so without this resampling trick, and executing this again. Then this takes a while, but essentially you will see that, or you can come back later, you will see that indeed now after taking out the resampling, your class balance is completely broken. Okay, so to summarize this example, so I constructed this input pipeline using 2 random queues and read data from multiple root trees asynchronously, and also performed on-the-fly preprocessing, in this case, random sampling of the tensors. So outlook, the presented root TensorFlow pipeline is a kind of proof of concept that you can directly interface these 2 big libraries. Unfortunately, this queue system is deprecated now in the new TensorFlow 2.x version in favor of the new dataset API. The main drawback from the queue system is that if queues are closed, so run dry essentially, they cannot be reopened. So always you need to recreate this session, which was always an annoying feature. I'm currently working now on adapting to the new dataset API system. An intermediate problem is that linking TensorFlow and root together is quite complex. Now running into ABI problems there, because I'm just taking the binaries as they are in the Anaconda repositories. However, on a side note, maybe it's not even needed to install all of root anyway. A slim C++ wrapper just for the IO library of root or IO part of root would just be suffice. Maybe someone from the audience even knows or can point me in some direction that could be helpful for this project. So now just let me check. Maybe you can. Yes, exactly. So you see here now that after taking out the resampling, that indeed now the class balance is not given anymore. Okay, so then I come to my last slide. So to summarize, I showed you the basic ingredients, how to train a neural network, how you feed data into TensorFlow, and then how one can use this generator pattern to use uproot and then feed data sequentially into Keras into TensorFlow. I introduced you to the TensorFlow queue system and how to use a custom operation to interface TensorFlow with root directly. And this, as a proof of concept, actually works for training neural networks directly on root T-trees without any conversion or using intermediate formats. And it's also very flexible. You saw that one can easily select the branches one wants and also perform preprocessing, and one even does not need to worry about any multi-threading. It's all taken care of by TensorFlow. And this pipeline, if you want to know more, this was even used in a real publication with CMS in a search for long-lived particles decaying to displaced jets. Thanks.
Thank you for this nice presentation. It seems you don't have so many questions. I see one. There's another one. I will share this.
Should I stop? Or?
I can overwrite you, no problem.
Okay.
Okay, so I'll read it. So the first question was, how much more performant is the C++ reader in root compared to uproot? Have you tried this?
So as I said, the nice thing is that you don't need to worry about parallelism, so that you spawn your threads and everything properly. So this is a clear advantage, because of course you can achieve the same with uproot, but you still would need, as I showed you, you still need to write some kind of system that runs asynchronously to your training on the GPU, that just is there for reading multiple files asynchronously, populating some kind of cache, and then also do some random sampling or pre-processing, also random selection of the batches. So I guess you can, if you're really good, you can definitely write the same system just with uproot, sure. But then you really need to know how to do these thread things very carefully.
Mm-hmm. Okay. Then the next question is, does resampling in this context correspond to changing the distribution of the training data in PT and eta, while keeping distribution, giving PT and eta unchanged? I also was not sure how this resampling works.
Yes, no, so sorry, maybe I did not explain it in too much detail. So no, the resampling is really done as a 2D distribution. I only showed you the PT. Yeah, it's essentially really resampled in such a way that at each point in PT and eta, you have the same number of classes.
Okay.
So the distribution, the input distribution really changed. Yeah. And the goal is really that the network cannot learn or cannot exploit differences in PT and eta. Mm-hmm. Because if you think about, say, for example, you want to train just your classifier BJet versus UDSG, you would use QCD and TT bar samples. This is like a standard thing to do, while TT bar, usually the BJets have much higher PT than what you usually find in a normal QCD sample. And so the network will just be biased towards higher PT because it thinks there are more BJets at higher PT, but for a general tagger that should be used by all analyses, this is not well generalized. So that's why this resampling is done. But please have also look into the publication there. So it's more explained in more detail.
Okay, the next question is, you have mixed root uproots, root plots, and outlook, and or simply an opportunity to try out the various tools while working? So yeah, that's actually a good question.
Yes, so so I can also say that I don't want to do this because it's quite painful to find matching versions that work together. But the interesting thing here, I think that that you can interface TensorFlow with root and then have this pipeline. That's really a nice way to be much more flexible in your training cycle, especially if you start developing a neural network. You don't really know, okay, what kind of input you want to really use or try out. Then always going through an additional step of first converting things back and forth through different formats. This is really like a showstopper a bit. And really not quick. You don't have a quick turnaround in this case. So yeah, I mean, interfacing TensorFlow with root is tricky, but it can be done.
Okay, I see no more